Hello, my name is Brinton. I'm a second-year PhD student in the Edge Lab at Princeton. Today, I'd like to talk to you about a research initiative going on in our lab, Topology Optimization and Power Distribution Networks. Let's start this presentation by looking at three perceived problems with current power distribution systems. The diagram on the left shows a typical layout of an electric system, especially in the United States. What we notice is a highly centralized hierarchy. We have a small number of large generators that are responsible for serving all the residential consumer demand in the grid. Centralized hierarchies have advantages in terms of economies of scale, but they're also presenting problems with sustainability as well as resiliency, meaning that if we have the outage of a single generator, it could cause rolling blackouts in many portions of the grid. As a result, there's recently been a push for more distributed forms of generation. Coal, natural gas, and nuclear make up almost 90% of the generation in the United States. Now, you're probably wondering why this is, since these are also the most harmful forms of energy to the environment. Well, it turns out that there are also many problems with renewable energy. One is cost. The cheapest of them is wind, which is significantly more expensive than traditional. Second is unpredictability, since they vary over time. And third is bias, since they're not favored by the generation companies. The third problem is with transmission congestion. Population increases will naturally lead to influxes of load demands. For instance, the United States is expected to increase almost 20% by 2030. As a result, we will need more generation capacity. The research question we pose is the following. Is it possible to achieve a more distributed topology, more green sources of energy, and more generation capacity simultaneously? These three have been considered, but not yet under a unified framework. Our problem formulation is as follows. We'd like to augment current grid topologies to the following goals. 1. To distribute the added generation capacity. 2. To use renewables. And 3. To minimize total cost, meaning transmission cost plus generation cost. The idea is that we want to offset increases in the generation cost that come about by using renewable forms of energy, by seeing the corresponding reduction in the transmission cost obtained by optimally placing and sizing those renewable energy generators. It turns out that this problem becomes non-convex as well as stochastic, which makes it quite difficult to solve. Convexity, roughly speaking, is a watershed between a class of easy problems and hard problems. So if your optimization problem is convex, there's a class of algorithms that can be used to solve it efficiently and quickly. Stochastic means that we're dealing with non-deterministic variables, those that depend upon exogenous information to the system. On the right-hand side over here, we show a diagram to illustrate the optimization from a high level. This bus right here in red is a wind farm that we want to integrate into the grid. What we don't know is its capacity, where exactly we want to place it, or its grid coordinates, as well as which of the pre-existing buses we would like to connect it to. Those are all outputs of the corresponding optimization problem. This shows the sample output for a single generator. In the base case, we have a 30-bus transmission system, which is shown in the black. The red over here shows a suboptimal solution that we might obtain if we just eyeball the placement. These red dots show connections to pre-existing buses that we might make. It turns out that this is more expensive than the optimal solution, which is shown in the green right here. That optimal solution can reduce the transmission cost by 15% over what it was in the base case, even before we increase the demands. This shows the sample output in the case of 4 generators. The situation gets even better when we include more and more generators. In this case, we have buses 31, 32, 33, and 34 that we've added with the corresponding connections color-coded. In this case, we can reduce the transmission cost by 50% over what it was in the base case. So as we distribute the capacity more, we see more reduction in the transmission cost in addition to more resiliency to outages. Our research goals can be summarized in 4 main statements. One is to quantify cost benefits that we can obtain by distributing the generation capacity, which we just looked at in the last slide. 2 is to incorporate stochastics into the analysis by modeling solar and/or wind forecasts, for instance by Markov modeling. 3 is to develop efficient optimization problems to solve our problem without sacrificing solution accuracy. And 4 is to incentivize collaboration with independent system operators and regional transmission operators to obtain their topology layouts and apply our solutions to their realistic situations. Thank you for listening. If you have any questions, please feel free to email me. My email is cbrinton@princeton.edu.